Welcome to lecture 21. In the last class, we have derived the one-dimensional consolidation equation, which will predict how the pore pressures get dissipated in soft clays over a period of time. To illustrate the requirement or the usefulness of this solution, let us look at a practical problem. We have a thick deposit of soft clay. Let's say H can be anywhere from 5 to 15 meters or whatever it is, and you are going to apply a uniform load, and the width of the load is fairly large. You can say that B is greater than H, and here you have a clay or a fine grained soil, let us say, and on top we have sand, and on the bottom also we may have a sand deposit. This clay layer has a permeability which is equal to K, and coefficient of volume change is M sub B. So when you apply this load, what happens to this clay layer? In practice, you may wonder, where is it necessary? I have a site near the coast where the sea level, the groundwater level, tidal 1, sea level, they are all very close. So I would like to raise the ground level to, this is what we call finished ground level. This is the existing ground level. I may put in 2 to 3 meters of fill so that the finished ground level is higher than the existing ground level, which is at the sea level or the tidal level. And if you do that, what we have done is basically added 2 to 3 meters of weight, which can be, Q will be 2 into, let's say, 18.5, that is 37 kPa, or if I take 3 meters into 18.5 will give me 55.5 kPa. That will be the uniform surcharge, and you have the clay layer here, which is of some thickness H, could be 10, 12, 14 meters. Or you can think in terms of, I have the ground level here, I want to build a 4-lane highway on an embankment. So this is the 4-lane highway, and the embankment slopes are 2 horizontal is to 1 vertical, 2 horizontal is to 1 vertical. Say this is about 15 meters, and the embankment height is 3 meters. Then I can say this will be 12 meters, and this will be 12 meters. So the total base width of the embankment will be 15 plus 24, that gives me 39 meters. And here I have a clay deposit which is only 10 to 12 meters. You can again see the thickness is smaller than the width of the loaded area, or you also look at some of these liquid storage tanks by Indian Oil or Bharat Petroleum. The largest one is in Hazira, which is, I have a soft clay here about 12 meters thick, and they have constructed a liquid storage tank which is 82 meters in diameter. The diameter is 82, and you can again see that the loaded area is much wider than the thickness of the layer, in which case there can be no flow laterally, and whatever dissipation has to take place will take place to the bottom and the top, or if the bottom is impervious, only to the top. So you can see these are all examples of one-dimensional consolidation. The flow can be only in the vertical direction to the top and bottom surfaces, or to the top alone. How do I represent this in the laboratory? If I want to simulate a field condition of one-dimensional consolidation, we go back to our odometer. If you go to the odometer, you have seen we have a soft clay sample inside a ring whose diameter is 50 to 75 millimeters, and the thickness is about 20 millimeters. Maybe in some cases 25, but usually we start with. Then what we do, we provide a filter paper and a porous stone, and a filter paper and a porous stone. And if you now apply the load, all the load is acting on the sample. Because of steel ring, there is no flow radially and no deformation. No flow laterally and no deformation. So this exactly replicates the one-dimensional consolidation phenomena in the laboratory. And that is how Terzaghi developed this technique, so that we can study what is happening when you have a large loaded area being acted upon by uniform load, and we have a soft clay deposit whose thickness is less than the width of the loaded area. In the last class, we have derived the governing equation, a partial differential equation satisfying several conditions. The governing consolidation equation, one-dimensional, is derived from first the continuity condition, then the stress-strain relationship. Can I say here this corresponds to K by gamma W into delta square U by delta Z square is equal to minus delta V by delta T. The amount of flow going in minus amount of flow going out is equal to rate of change of the volume per unit volume. This one is nothing but, we said A sub V is delta E by delta sigma, and we converted that into M sub V, which is equal to A by 1 plus or E naught, you can say that. So that if I want delta sigma by delta E, it's nothing but 1 by M sub V. The third one we used was the effective stress equation, which says sigma is equal to sigma prime plus U. The total stress is equal to effective stress plus the pore water pressure. When I say this, actually you should have used EUE, which means excess over hydrostatic, but we generally drop the subscript, but we know this is the excess over hydrostatic. We have pore pressure due to hydrostatic, that is natural static groundwater level. That is not going to contribute any consolidation. Consolidation is only because of additional load that we put in. If you combine all of these principles, then we will arrive at the partial differential equation which we derived last time, which is a very simple one to write. We say that derivative of u with respect to t is equal to c sub v derivative of u with respect to depth, second derivative. Cv is called the coefficient of consolidation. It's a very interesting parameter. It's related to permeability by unit weight of water and the coefficient of volume change. This is coefficient of permeability, and this one is coefficient of volume change. So we call it as a kind of a coupled parameter. It is combining a hydraulic property with a mechanical property, which is nothing but stress-strain relation. So coefficient of consolidation is a reflection of both flow and deformation. And consolidation is called a coupled phenomenon. The deformation occurs after the flow starts or dissipation of pore pressure occurs. Now you have seen that this is a second order partial differential equation. There's a derivative with respect to time t, which means I need initial condition. I need one equation, and we have second derivative with respect to z, so we have boundary conditions. I need two of them. And how do we satisfy? Here is the clay deposit of thickness, let us say 2h. Please note that the total thickness I am saying is 2h. You have a pervious stratum on top, another pervious stratum on the bottom of the clay layer. This is the clay layer whose properties are K, MV and CV. At t is equal to 0, we set the pore pressure. If I plot, I am measuring Z from the top. So if I plot Z and 2H, you will realize that pore pressure is the same everywhere over the whole depth. How did we arrive it? If you remember, we looked at the cylinder with a piston and we put a spring here. If you now apply load at t is equal to 0, when you apply the load, the fluid does not compress, does not escape, so all the load will have to come to the pore fluid. So if the area of this is A, pore fluid U is equal to P by A. Similarly, if I am applying a uniform surcharge Q, Q U naught is equal to Q. Suppose you are putting 50 kPa, 60 kPa at T is equal to 0, the pore pressure is equal to whatever is the applied stress, 50 kPa or 60 kPa. Then let's look at the boundary conditions. Here, this is the top boundary, it's next to a highly pervious medium. So we say at Z is equal to 0, U is equal to 0 for T greater than 0. Please remember, you have to start the clock. When you apply the load is equal to, or the pore pressure is equal to the applied stress. But once you say we want the consolidation to occur, this point is right on the pervious boundary. So the dissipation will be immediate and the pore pressure will become 0. Similarly, at Z is equal to 2H, U is equal to 0, T greater than. And here we write for 0 less than Z less than 2H. Fortunately, the same thing holds good for one phase drainage. Only thing is, in that case, the thickness is equal to H. And if you now satisfy from your mathematics, you will be able to derive the solution through a technique called variable separables. Solution of the partial differential equation can be obtained very easily, saying that U is a function of T and a function of Z. I will not derive the whole thing because it becomes too elaborate. You will find it in a textbook or from your own background in mathematics. You can say U is equal to U naught sigma I going from 0 to infinity 2 by pi or 2 by m, sorry, sine 1 plus mz by h e to the power of minus m square. It's an infinite series where we write pore pressure at any time at any depth is equal to initial pore pressure times sigma I going from 0 to infinity 2 by m sine mz by h into e to the power of m square into t. Here m is nothing but 2i plus 1 into pi by 2, and t is called the time factor, which is equal to cv t by h square. Coefficient of consolidation times t is the real time. It could be 1 day, 1 month, 1 year, etc. Or in the laboratory, you say 1 minute, 1 hour, 10 hours, 12 hours, etc. H is the maximum length of the drainage path, is equal to half the thickness of the layer in case of two-phase drainage, and equal to the thickness of the layer in case of one-phase drainage. So that is because in case of two-phase drainage, half the layer drains to the top, the bottom half drains to the bottom. In case of one-phase drainage, the whole thickness is used for drainage. So please remember here, I can go from 0 to infinity, which means when I is equal to 0, you will get pi by 2. When I is equal to 1, this becomes 3 pi by 2, etc. So what you find now is that pore pressure is a function of depth, and you can see it's a sine function and multiplied by an exponential function. Let us see how the plots look like. It's very interesting to study this phenomenon. We have the deposit here, 0 to 2h, and here is the midpoint h. Shall I say u by u naught, so that this becomes 1. Initially, the pore pressure is from A to B, which is 100%, at t is equal to 0, or time factor t is equal to 0. The moment you say t is greater than 0, or the time factor is greater than 0, the clock has started and the process of consolidation begins. this pore pressure immediately becomes 0. C and D. At the top, pore pressure becomes 0. At the bottom, pore pressure becomes 0. And then as time progresses, so this is equal to, let's say T is equal to time factor 0.01, 0.05, 0.1, I'm sorry, not 1, 0.2, 0.5, 0.2, 0.05, 0.1, 0.2, 0.5, etc. It is symmetric about the mid-plane because if you look at it, it's a sine function. At Z, if it is equal to H, you get a factor of 1. So sine is maximum when you have sine pi by 2 is 1, so you get that exact. And you will find that pore pressures are maximum at the center, they tend to decrease towards the edges. And on the two faces, it is always 0 because the boundary condition is U is equal to 0 for T greater than 0 at Z is equal to 0 or 2H. So what happened is the pore pressure dropped down to 0 and the pore pressure is high, so there is a gradient and the flow takes place, and once it takes place, the dissipation occurs. Now this is how the pore pressures are dissipated in a thick deposit, or in the laboratory. If you look at the odometer, it's exactly the same because the analogy is identical. What we are interested is not only the pore pressure dissipation, but we are also interested in the settlements. And we say the settlement can be found out saying settlement at any time t is equal to mv into delta sigma prime into the thickness. And I can say that it's mv. We'll come back to this a little later. Delta u minus delta sigma minus u into h. Because the effective stress is equal to total stress minus delta u. We can also say that mv into q minus delta u into h. Or you can say mv into u naught minus delta u at h. But these are functions of time t, so this is settlement at any point z. If I want the total settlement, I had to integrate 0 to 2h of this settlement, which is equal to mv u naught minus delta u, can I say z and t into dz. Let me write it as small element. If I write it, that becomes easy to understand. For a small element, I am writing and I am integrating to get the total settlement. The final settlement at t is equal to tending to infinity, the pore pressure is 0. So I simply get S final is equal to integral 0 to h mv u naught, or you can say q into dz, which works out to be 2h into, because u naught is constant, mv into q. That's it. mv, q and 2h. The new term we define now is called degree of consolidation. Degree of consolidation is represented by capital U is the settlement at any time t divided by the final settlement. So it becomes, that is, I can write it as st and s infinity. St tends to infinity. Now from these expressions I can write this is nothing but mv integral 0 to 2h u naught minus u z t delta z divided by mv into q into 2h. Obviously you can cancel this. Let us also simplify here. I can integrate here, which again gives me 2h. This is first term will give me u naught into 2h minus, I get integral 0 to 2h of u z t dz divided by this q. You agree that u naught is equal to q. Initial pore pressure is the same as the surcharge pressure. So we can cancel this and say degree of consolidation. If I divide this, I'll get 1. I'll get 1 integral 0 to 2h 1 by q, or I can say u naught u z t dz by 2h. And if you carry out this integration with respect to z and simplify, we will get degree of consolidation is equal to 1 minus 2 by m square e to the power of minus m square t. Again, you have defined m, which is sigma term, I going from 0 to infinity. M is equal to 2i plus 1 pi by 2. Again, you have the infinite series with respect to time t, so it becomes 1 minus I going from 0 to infinity 2 by m square e to the power of minus m square t. What you find here is a very interesting thing. This is e to the power of minus m square t. Look at m is equal to 2i plus 1, and m square is into pi by 2, so it becomes 2i plus 1 whole square pi square by 4. If I is 0, this is 1. If I is equal to 1, this becomes 3. Square of 3 becomes 9, and so you will have 1, 3, 25, etc. This term becomes very, very large for even small values of I. And the significance of that gets lost. That means the terms become very small, and we can approximate with our 1 or 2 terms. I'll just show you, but I want you to remember this relationship, degree of consolidation, which is the ratio of settlement at any time t by the final settlement. And why is it necessary? If you want to estimate the settlement at any time t, what we will do is u times final settlement. Final settlement is very easily estimated knowing the coefficient of volume change, stress increase, and the thickness of the layer. And if I want settlement at any time, I need to multiply by the degree of consolidation, which is governed by this equation. The time factor, once again, is CVT by h square. Coefficient of consolidation times the real time. Real time means could be minutes, hours, days, weeks, months, years, etc. And half the thickness of the layer in case of two-phase drainage, and equal to thickness of the layer in case of one-phase drainage. Instead of saying all that, we say it's equal to the maximum length of the drainage path. So that's how we can account for it. And again, to illustrate this, suppose I plot. Let us say you're plotting u varying from 0 to 100% versus time. It goes something like this. At t is equal to 0, u is equal to 0, and as t tends to infinity, u becomes 1, or I can express it as 100%. What happens? As t becomes large, e to the power of minus large quantity becomes 0. So this term becomes 0. So you will get degree of consolidation is 1 or 100%. This is how you will find it is decreasing. There are two quantities which you should remember. 50%, then t is equal to 0.197. And if it is 90%, t is equal to 848. These are two wholly numbers. I want you to remember T50 is 0.197 and T90 is 0.848. What does it mean? If the time factor is 197, we will get 50% degree of consolidation. Half the settlement is mobilized. If t is equal to 0.848, 90% of the consolidation is over. And you'll please remember the curve is very flat here, so it takes very long time for 100% to be attained. It's a long tail for this graph. The alternate ways of plotting this curve, There are two ways which are given by Taylor and Casagrande, one at MIT, another at Harvard, and we use them to calculate CV. Please remember, we said to get CV, I need K by MV into gamma W. But if I do an odometer test, I have no problem at all. I can get this coefficient of consolidation directly. So what Taylor did was, he plotted square root of time t. It turns out you get a straight line and then becomes a curve. Somewhere is 100%, this is 0. And you find that this straight line extends for quite some time. And what he found was, you can draw this line, and if I draw another line whose slope is 1.15 times the slope of AB, this is AB. I plot the points and I get slope here, and if I multiply the slope by 1.15, it hits corresponding to T90. So I get 848. So what Taylor said was, you conduct an odometer test. In the laboratory, we do a consolidation test. You take the ring and do all the thing and apply. Let's say you have increased the load from 50 to 100 kP. And I take the readings, T and dial gauge reading. So 0, 1/4 minute, T is in minutes, 1, 2 1/4, 4, 6 1/4, 9, etc. for one full day. I have all this. He says plot square root of time t, which means 0, 0.5, 1, 1.5, 2, 2.5, 3, etc. Now you know why we use these things. And you plot the points. Here I am plotting the dial gauge reading. And we fit a straight line. This would be the initial portion. It's a line AB, what you got there. Now draw the second line. Slope is equal to 1.15 times slope of AB. And now you get square root of T9. Let's say this value is something like 3 or 4, whatever it is, or maybe 20. Then I can say if square root of T90 is say 15, T90 is equal to 225 minutes. So you have found out the time for, real time for 90% degree of consolidation, and we know that it's equal to 848, the time factor. So you say T is equal to 0.848 is equal to CV into real time T90 by h square. In the laboratory, h is equal to 10 mm because 20 mm is the thickness, half the thickness is 10 mm. We know the time factor T90. I know the real time factor here. I can get CV. CV is equal to coefficient of consolidation 848 into h square divided by, it's very easy to find out from a simple experiment. All I need to do is plot whatever data you have on a square root of time versus settlement, and you will get CV. Another method which is given by Casagrande is slightly different. What he found out was, he is plotting now, U again goes from 0 to 100, but here he plotted log time factor. So it starts with 0, 0, 1, 0, 1, 0.1, 1 and 10, something like this. The curve is an S curve in the sense initially it drops down and then after some point it becomes asymptotic to the 100% line. And what he found was this is 50%, so T50 is equal to 0.197. So he looked at this characteristic. Instead of plotting settlement with respect to square root of time, what we will do is we'll plot settlement or dial gauge readings as a function of log time, real time. I'm plotting here log t, so which means I'm starting with point 1, 1 minute, 10 minutes, say in minutes, 100 minutes, 1000, and maybe you go up to maybe 10,000 minutes. And I'm plotting the settlement. It will start somewhere here, keeps going like that. Maybe a little more shape here. Because this is stretched, you get something like this. So if I know the initial value, this is at t is equal to 0, the settlement, which means S0. What we say is that this line, unfortunately, is not asymptotic to time factor, but it is continuing to deform. We'll come to that in the next class. What we do is extend this line back here and draw a tangent to the point of inflection. What is this point? You can see that above the point, the curve is concave downward. Below the point, the curve is concave upward. The curvature changes at this point, which means at that point, it's a, if I draw a tangent, this tangent is to the right of the curve above and to the left of the curve below. If I do that, I get what you call as S 100% primary consolidation. And if I know S0 and S100 for primary, I can immediately pick up 50%, and with respect to 50%, I get T50. Let's say T50 is equal to some 18 minutes. That means after 18 minutes, 50% of the primary consolidation is over. And again, you go back to T50, which is equal to 0.197, is CV into T50 by h square. So CV is equal to 0.197 h square by T50. So this is called the Casagrande method. Whereas the previous one was called Taylor's square root of time method. So we have two methods of calculating CV from the odometer. If I use Casagrande's, I use 197 into maximum drainage path square by T50. And if I'm using Taylor's method, CV is equal to 0.848 T90 by h square. You determine T90 from the square root plot, and h is the maximum drainage path. We can easily get the coefficient of consolidation. So this is how we try to determine CV from laboratory test.